Well, good afternoon, Alice, and thanks for taking part of this interview. The first question I have for you is about the topic of your talk, which was about universality classes in random matrix theory. So, could you describe briefly those concepts?
Yes, with pleasure, Rodrigo. So random matrices are big arrays whose size is going to infinity, and you imagine that the entries are random. And this topic appears first in statistics, actually, when Wishart was trying to analyze big arrays of data. So that's the idea. You have a big array, the size is going to infinity, and you are trying to figure out the properties, for instance, of the spectrum of these random matrices. And so then afterward, this object showed up in physics in the work of Wigner and Dyson, who used random matrices to model the Hamiltonian of heavy nuclei. And then in operator algebra, in number theory, now in machine learning, so in many fields, this type of object appears very naturally. And so the question of universality class is you would like to understand the properties of this object, but it's quite complicated, okay, because the spectrum is a complicated function, for instance, of the entries. So even though you have maybe a very easy model assumption on the entries, like they're independent, on Gaussian, the eigenvalues will be complicated to compute. And so what turns out is that we can often do that for very specific models. And then we try to understand the other models by comparison. So we talk about universality class when several models satisfy the same type of properties. Like we would like to say, which are the matrices which have local fluctuations of the same kind as Gaussian matrices, for instance. And so this will be the universality class of Gaussian matrices. So this is what I try to describe in my talk, which kind of properties of the matrices give you which type of either global behavior or fluctuations or rare events.
Oh.
And also, yes, maybe what I tried also to emphasize is the role of localization in this type of universality classes.
Can you describe a little bit what do you mean by localization?
Yes, so for instance, I tried to give the image of the central limit theorem. So if you have entries which have all a finite second moment, and you sum them and you divide by square root of n, you will converge towards a Gaussian. And so in this case, this means that all the entries will be roughly of order 1 over square root of n. So it's delocalized. Yes. Whereas if you start to sum entries which do not have a finite second moment, then somehow what will happen will be that you will have lots of small entries when you renormalize properly your sum, but you will have a few big ones. And so this is what we call localization. And the same phenomena appears for random matrices, but of course it's much more complicated to understand how is localization showing up. And so I try to advocate somehow that we can still see this kind of phenomenon like the eigenvector will localize. So it will not have all small entries, but a few big entries and lots of very small entries. That's the kind of localization we can try to look for.
Oh, interesting. You mentioned, a little bit about the beginnings, the type of that Wigner shows a specific type of matrix model. Is this sort of like an analog of the Gaussian for like a random variable in this case, or what is like the analog version of the Gaussian for random matrix?
So the analog is really maybe a matrix with Gaussian entries. It has more symmetry. It's like the Gaussian variable. It's one of the variables which have the most symmetry, and because of that, it has lots of specific properties. But then, of course, you can. So what Dyson and Wigner said is that when they want to model the Hamiltonian of a physical system, they will try to find out what are the symmetries of what they're trying to model, and then they will take the model, the random matrix, as random as possible, within the fact that they should satisfy these symmetries. So like this, they had several models, but in general with Gaussian entries, but you could have Hermitian or symmetric matrices or symplectic matrices. So all these kind of models were corresponding to different physical properties. And maybe a last point, which is nice, which is that this type of model in physics are kind of related with so the Gaussian entries, which are kind of the simplest, because when you sum Gaussian variable, you still get a Gaussian variable, so it has lots of nice properties. But in fact, so when the size of the matrix goes to infinity, you can think about your matrix as a big operator in infinite dimension, and then if you look at it like this, it's like in free probability where you get what people call the semicircular operator. And in free probability, this operator really plays the role of a Gaussian variable. So you have a notion of independence, which is now freeness, because you have to think that now you have variables which are non-commutative. And within this framework, really, you have to think that the limit of these Gaussian matrices is a semicircular operator, which really has the same role as a Gaussian in classical probability.
Interesting. But this connection was discovered more or less with the development of the theory of random matrices, or was independent?
So it came somehow with the development of free probability. So free probability was introduced by Voiculescu in the 90s. And he was really developing this theory for application in operator algebra. And then he defined this notion of freeness, which is really related with the notion of freeness in groups, but in this kind of non-commutative probability theory. And then at some point he discovered that there was a very nice relation with the usual notion of independence, but if you take matrices with Gaussian entries which are independent, then at the limit of their size going to infinity, they will be free. So somehow you can see free probability as a kind of limit of classical probability, but when you plug in these large random matrices. So this came after the beginning of the theory of random matrices. You can date it back to Wishart. It was like 1926, and free probability was like 1993 or 1990, something like this. So it was later that free probability came up.
I guess there was more like development.
Yeah, of course. So there were more developments, but I would say that really the theory of random matrices blew up in the 90s, really, because there were free probability, but also there was investigation of the local fluctuation that I mentioned for Gaussian ensembles, which were done by Tracy Widom and Mehta. So there were a lot of developments, and since then there were a lot of new results, in particular about these universality classes. But I would say that, yeah, the field has been really blowing up since the 90s.
Oh, that's, yes, a quick remark or question about how difficult it is to move beyond Gaussian, like in this context.
Oh, that's really, that's not easy. So as I said, there are lots of open questions if you think at Evitels matrices, like we don't know how the eigenvalue are fluctuating within the bulk. But also to get to universality, I mean, very fine and precise analysis had to be developed so it was by these two teams of Erdős, Schlein and Yao, and then Tao and Wu, and there were a lot of beautiful papers, and it really used a very fine analysis. I mean, I tried to mention it a bit, but somehow the first idea was that to go beyond a Wigner result, which tells you the asymptotics of the spectrum, you have to make sure that this kind of asymptotics still hold if you look at a finer scale. Okay, so if you look at really small intervals, and then the idea was if you can go to a very small size of intervals for your convergence, nearly at the size of the fluctuations, then you can compare the models together. So this means that you have two steps somehow. You imagine that you have a big picture, macroscopic picture, the convergence of the eigenvalue at the wall. Then you take a microscope, you blow up, and you make sure that somehow this convergence still holds on a finer scale. But you cannot really go that way up to the fluctuation. You can go just above. And when you are there, hopefully you can have another argument, and there were several different types of arguments which were proposed to do that, to really get to the level of the fluctuation and show a comparison with the other model. So that's really, that's not an easy thing to do, but now it's quite well understood, but there has been a lot of work since, I would say, 2010 or something like this. Yeah.
Interesting. The last question, more related to the future, for like prospective students interested in the field of random matrix theory, what topics should they focus on, and what interesting developments are occurring that maybe they could get into in the future?
Yeah, so I think that there are lots of nice new connection which has been made, for instance, with statistical learning. So in neural networks, you can eventually see the role of large random matrices. There are also tensors and relation with quantum information. So there are lots of new relations which really will call for new analysis on new results. So I think here there is a lot to do. So I would say to a student that it's good to learn random matrices for the theory, but to apply it eventually to this type of new fields which are just now blowing up.
Yeah. And quick question, what big problem would you want to see resolved in the next 10 years?
Yeah, so I don't, there is still big problem. So now I have a ERC grant, which is about these large deviations and large random matrices. And one of the cornerstones is to understand what we call the Voiculescu entropy, which is this entropy that Voiculescu defined in the context of free probability. So this is still very poorly understood, and we are still trying hard to understand that. This is kind of the Graal, but there are lots of difficulties still ahead, so who knows, maybe. But it's a problem that I have been thinking about for already 20 years, so hopefully, hopefully one day. But on the way, there are lots of other nice questions. So just now I have lots of projects around this large deviation question and large random matrices, which apply also in statistical learning or to understand the complexity of complex functions. So that's kind of the question that I am thinking about just now.
Well, let's hope it goes true.
Thank you. Yeah, I hope so. Thank you.